wait, now I have a line to stuff in my head.
All right, today's going to be really laid back. We just have 2 more questions to go over from this section, which means the rest of the day I can give you to work on some of the homework problems. Okay, if you go on my teacher page from the school's website, have you visited some of those before? Have you stalked some of your other teachers? No? No? Okay. Well, I think you guys know in the past I've used Schoology, but the district is really pushing these teacher sites. I have no issue with it, okay? But that's going to be where you go to get some homework solutions. Okay, so Schoology, no more. I mean, not completely no more. If I need to use it, I will. But on my teacher page on the school's website, you can go to the BC course, and I put the odd solutions online. Okay, so you can check your work as you go. So when we get done with these 2, I'll let you work on some of the homework problems together, and if you need to ask some questions, you can do that. Okay? So we've been looking at these cross-sectional pieces of these particular regions and figuring out if a region had a particular cross-section, what would the volume be of that solid formed by the cross-sections. We looked at Play-Doh activities. If you look at some of the ones we did last week, we did one region with all these different cross-sections if it had those particular shapes. What we're going to take a look at today are 2 kind of trickier type problems that might show up or might be phrased weird. So let's go ahead and see how these operate. An oil spill on the surface of the water has a surface shape of R. So this region R is, if you were looking at a pond, okay, this would be the pond, the top of the pond, okay, the surface of the pond. And defined by the intersections of sine of x and then this other sine function. So graphically we should be able to figure out what those are since we have a calculator. The depth of the oil spill at each value of x measured perpendicular to the x-axis has this particular depth. We're going to find the volume of the oil spill. So in terms of this idea, it's almost like if you took our Play-Doh activity and it's now upside down. Okay, so this is the surface of your water, and then the oil is dripping down, causing this particular cross-section, whatever it is. Okay, so it might be a little hard for me to draw on here, but at this particular x value, if the oil was to drop a certain depth all the way through that x value, okay, keeping it the same all the way through, what would the cross section look like? Okay. It could be a square, okay, or a rectangle, right? If the depth was the same as the distance in region R, then it wouldn't be a square, but the depth might not be the same. So this is some type of rectangle. How do you figure out the area of a rectangle? Length times width, base times height, something like that. Okay, so in terms of our volume, we need to integrate the area of this rectangle. Okay, so one of the pieces we need to identify is that length, and then the other one would be that width. So how do you think we can label the length? Notice how that's the distance between the top and the bottom piece of the surface of this water. Can we perhaps label which equation is which? Which equation is the top function, which one's the bottom for this pond? Go ahead, Caitlin. Sine is the top one. and then the opposite of sine equation would be the bottom one. Okay, so to figure out or identify the length, we would need the top function minus the bottom. So we would have sine of x minus that negative sine function, so that would actually change to a plus. Okay, so that's your length. And then we need to multiply that by the width, which in terms of this scenario is the depth of that oil spill. And they give us that function 2 cosine of x over 2. Okay, so to figure out the volume of this spill, we have to integrate the area, the area of the cross-section of the spill, length times width. Now we got to figure out those intersection points. So if you have a graphing calculator handy, let's go ahead and graph the two functions and go ahead and find those intersection points. Are we okay with where that integral came from, those two functions, length times width? When you think you have an intersection point, can you let me know? Go ahead, Eric.
I have it from 0.2617 to 3.4.
All right, 0.2617.
Yeah.
Okay. You could do 0.622, 0.621. All right, so from there it's just a calculator work, which can be tricky because we have a ton of parentheses and fractions to deal with. Just be very cautious. Any takers? What do you think, Cameron? 4.435. Now we don't know if this is cubic feet, cubic meters. They don't really give us a unit, but nonetheless it represents a volume. Make sure you're in radian mode too, because we're dealing with trig. Work out? All right, let's go ahead and check out the last one at the bottom. Our region R, defined by the intersections of these graphs, is the base of a solid. For this solid at each y, the cross-section perpendicular to the y-axis. Okay, so this is a little different. If you noticed in the last one, it said perpendicular to the x-axis. And notice how the cross-section I drew went the 90-degree or opposite way, opposite reciprocal slope of the x-axis. So this one's going sideways. Okay, if you think about your Play-Doh activity, instead of putting them this way, we would have put them this way. Okay, so perpendicular to the y-axis has this area. Find the volume of the solid. Okay, let's maybe graph all these different functions to at least visualize the region we're working with. Alright, so y equals 5x, we can graph that line. Start at the origin, up 5 over 1. We can graph the other line. All right, y equals 0 is the x-axis. So it looks like the region that all of those enclose is the bottom one towards the x-axis. This time our cross-sections are going perpendicular to the y-axis, so they're going horizontally. Okay, if you can imagine putting your Play-Doh or your paper in your Play-Doh going this way, that's how we're placing each cross-sectional piece. Do we know the shape of these cross-sections? No, this one's a little different, okay? It doesn't specifically say square or rectangle or semicircle, but what it does give us is the area of the cross-section. And technically, this is all we really need, because in order to figure out the volume of this region, we have to integrate the area of the cross-section. So let's go ahead and integrate that y squared plus 1. This would be a dy integral because we're perpendicular to the y-axis. So we just got to make sure that the bounds on this integral are in terms of the y-axis. So this little region R here, where does that region begin and where does that region end? What do you think, Eric?
0 to 2.8846.
All right, so we have to figure out that intersection point. Did you do that on your calculator?
Yeah.
What was it again? 2.8846.
2.8846.
2.8846. Oh, 88, sorry. Perfect. Could we figure out the intersection by hand? Yeah? Notice how we'd have to set this red equation and the green equation equal to each other. So that would be the 5x equal to the negative x over 5 plus 3. Okay? So you could work through that by hand. If I did that real quick, I don't like dealing with fractions, so I'm going to multiply everything by 5. And then subtract the 15. Or maybe I'll add the x. And then you can divide the 26. Okay, but notice how that's the x coordinate, right? Okay, if we want the height in terms of the y-axis, we would have to plug this in to either equation to figure out the y. I think this equation is a little bit easier. If we were to take this x value and multiply it by 5, the y value, 15 times 5 is 75. So 75/26, I bet is the same as 2.8846. Okay, so go ahead and you can let the calculator do the work from there. Let's go ahead and find our volume. Any ideas? Good, Eric? 885.4. Okay. 10.885, maybe. If you did up here 2.885 as your bound, maybe you got 10.886, okay, in some cases. But any of those would be fine. Can we get that value? All right, how are we feeling with these cross sections? Pretty okay? I think the Play-Doh activity helps. If you always go back to that as a visual, I think that helps. Okay? So you can go ahead and pick up with some of the homework problems wherever you are with those. I'm thinking the homework will be due Wednesday. Okay? Odd Solutions are online, so you can check your work as you go. If you want to go over any of them tomorrow, we can. We can go over any of them today if you want to, together. Okay? But I'll let you guys work on them from now.